Hello everyone, welcome back. Today we want to learn about series, what that means and how to do them. So our goal is to understand the properties and notations of a series, making sure to get the foundations right, and then be able to find the values of a series. Before we get to series, let's recall, or if you haven't learned this before, what a sequence is. So first off, a sequence is some list of numbers. Usually it's an ordered list. It could just be a list of random numbers. That would be a very a very interesting sequence. The sequence is usually a list of numbers. So first, let's come over to the left, or the right rather. It's a really basic sequence. One example would be the counting numbers. Okay, so the counting numbers, we're going to start with 1, 2, 3, 4, and so on. These three little dots means we keep on going. Okay, so that's the example of a sequence. Okay, but a sequence could be more interesting. Another example could be this. So sometimes we'll write a sequence in this way to when we call the letter A, maybe we're starting the A just kind of stand in whatever number it is, and have this letter N. So N just kind of indicates what this indicates is at some position N, some number N. That's what tells what A is going to be, and we'll say that A N is going to be equal to N plus 1, where N is equal to 1, 2, 3, and so forth. Okay. So this is an example of a ordered or generated sequence. What does this mean? Well, we're going to start with N. N is going to be what's called our index. We're going to start with N. N first is going to be 1. So I have 1 plus 1. Okay. When N is equal to 1, 1 plus 1 is equal to 2. Okay. Then we keep going. So go to the next number. N is equal to 2. 2 plus 1 is equal to 3. When N is equal to 3, we have, there's 3 plus 1 is equal to 4. And you keep going just as long as you want. When N is equal to 4, of course, it's 4 plus 1, which is equal to 5. So the sequence is, so it's going to start at 1. So N equals 1. So it's going to be 2, 3, 4, 5. And once again, you get the idea. Okay, you can go along as far as you want. So these are just samples of sequences. Okay, so basically, just as simply, you have some formula, some recipe, if you want to call it, to how to generate each term of the sequence, usually starting what's called an index. Okay, and then you just create your sequence, do as many as you want, and it may stop somewhere and it may not. It could go on forever, like the counting numbers go on forever, but you can also stop. So that's the idea of a sequence. Now, let's stop at the next term. The focus of this video is a series. Okay, so a series is basically if you take the elements of a sequence and add them up, you sum them up. So in math, if you see this notation, this is the notation for a series. Let's come over here and take a look at it. I explained it in the reading here, but let's actually do this. So if you see this, okay, like here, the ends kind of means something different. Here, the end before my sequence was kind of like each individual value. Here, my end means something a little bit different. Okay, so first off, if you see this big Greek letter, this means we're going to have a series. Basically, that means whatever these terms are, these numbers, we're going to add them up. The I is what's called the index. That kind of tells you where you are in your series, what number you're on, what section you're on. And once again, here the I appears here, and then the N is basically where the sequence, where the series ends, or the index ends. Okay, so usually the index starts with some number like 0 or 1. Of course, it could also be negative in some cases, but start with the basics. So we're going to start with 1, and we usually have some kind of formula or something, once again, like we saw before, to tell us what each element is, each part of the series is. And this is called the element. It has a formula that tells us what that is. And then Once you write that down, you then go to the next one. So I starts with 1, find out that element, then add that to make I equals 2, and so forth. Okay, then we end with n. Well, let's do a really basic one to kind of explain how this works, and then we'll talk about some more details of series. So let's say this example, let's say we want to do this series. So I equals 1 to 3 of just simply I. Okay, the letter I. Let's see what this means. Okay, so this can be equal to, so when I is 1, our element of that sequence or series is just simply 1. Okay, plus, since it means we're adding, the biggest called the Greek letter sigma means we're adding, and go to I equals 2. And then the next element is simply 2. Then, once again, we go to the next one, I equals 3. When I equals 3, this is just tells us it's 3, and so then we stop. Okay, so once again, this element right here is when I is equal to 1. You get this one, I is equal to 2. You get this one, when I is equal to 3. Okay, and because we have a 3 right here, I'm sure there's a better 3, means we stop. Okay, we stop at 3, and then finally we add these up, and that's going to equal 6. So it's much like a sequence, except in this case, we simply add up all the terms. And so this is the value, this is the result of this series is 6. Okay. That's just a very basic example. See some more basic examples here in a moment. Now, let's actually go back over here to the left. All right. So basic series. So now that we get the idea, this is kind of a notation, a more mathematical way of writing it, what this means. So once again, we see the big sigma. That means we're going to add something, add these terms. Our term here, we just keep calling it AI right now to make it general, meaning whatever we want to be. Our I index starts at 1, and it goes to n. And once again, n is also general in this case, which means you take element, when I is 1, you make A1, where that turns out to be. Then you increase your index by 1, you go to A2, add that to plus A3, and so forth. And these 3 dots means you keep on going until we get to A to the n. In this case, if n, this is called a finite series because it stops. It comes to an end at whatever number n is. Like this one came to stop at 3. Now, we can also have an infinite series. It's the same idea, except we never stop. So we have an infinity up here on top, but that means we never stop. Okay. So I actually just kind of expand this idea here. Let's do another example. Same series, except instead of going to 3 or some number, we go to infinity. So what does that mean? Well, in the same way, when I is 1, our element is just I, which is 1. Go to 2, when I is 2, our element is 2. Just as we did here, when I is 3, our element is 3. Then plus, then we just keep going. Okay, we do this forever. All right. Now, what does that equal? Well, this actually what's called diverges or goes to infinity. Basically, that means it just keeps on getting bigger and bigger and bigger forever. It never stops. Some of these series can actually end up in just a single number, actually a constant, which would be hard to believe, but it actually does, because you're adding just tiny bits on each step, and so eventually it all kind of settles down to a certain number. Okay, in some ways it's similar to like an irrational number like pi, which was, as you may know, the decimal place for pi goes on forever, but obviously it's a constant. It just ends at some point because those little bits you're adding just never, just kind of settles down to a number. So there's generally, in general, 2 types of series: a finite series and an infinite series. Okay, so now let's take a look at a few more examples. So here, let's just start again. Let's say, well, let's see. Actually, before we do that, let's talk about a few rules of series. So properties of series are properties of summations. Okay, so we're going to use these properties. These will actually help us then. This first one on the left. So here we have this series. And if you notice, it has a C. There's no I there. So it means it's independent of I. So what does that mean? Well, it means we're just going to, each step, we're just going to add up an I. Okay, so let's actually show some of these over here. So these properties. So the first one, series from I equals 1 to n of c. Okay, what does that mean? Well, notice there's no I here, so when I equals 1, our first value is c. Of course, it's a series, we add that to the next value. When I is 2, value is also c. Okay, go to 3, value is also c, and so forth. So plus dot, 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 plus up to c. And what we have here, if we do this, when we finally get to n, we have n c's. Okay, so we finally get to n, we have n c's, and of course that is just simply n times c. Okay, let's also do a quick example of that. So if we have this series, I equals 1 to, let's say, just make it a simple one, 3, okay, of 2. Okay, once again, what this means, when I is 1, our value is 2. Then we start over. The next value, I goes to 2. When I is 2, the value is 2. And we go to I equals 3. When I is 3, our value is also 2. Okay, and then, of course, that's n equals 3. We stop. So this is, of course, n equals 1, n equals, or sorry, I equals 1. I equals 1, I equals 2, then plus I equals 3. So we stop. Of course, that number is 6, which is equal to 2 times 3, okay, as we expected. Okay. Look at this second property. All right, this other property, let's call this number 1, property number 1. Property number 2 says this. So if I have this series, I equals 1 to n of c times ai, okay, well, how does this work? Well, let's go back and take a look at how we define this kind of mathematical series like this. Okay, so we do this, then when I is 1, our first term is going to be c times a1. But essentially, we're just going to add c to all these and multiply c by each step here. Okay, then when n is 2, this is going to be c times a2 plus dot, 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 keep going to the nth term at the end, which is c times an. Okay, now, you notice if we factor out, look at this, if we factor out a c, what we get is c times a1 plus a2 plus dot, 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 meaning you keep going all the way up to an. If you factor take a c out of all that, you notice this is simply this series. Okay, so this is going to be c times I equals 1 to n of ai. So that's where that comes from. That's why that's true. Now, let's do a quick example of that. Let me actually stop here a moment. Let me make sure I have enough space. While I'm here. Don't be alarmed. We're not doing this many pages. I just want to make sure I have enough space just in case I'm writing more than I expect to. Okay, so a quick example of this. So let's do just a basic one to get started. I equals 1 to 3 of 2 times I. Okay, so 2 times I. Okay, so once again, for I equals 1, our first step is going to be 2 times 1. Okay, plus for I, then go to I equals 2, and I equals 2 is going to be 2 times 2. Write a better 2. I messed that one up. And plus, when I is equal to 3, of course, that's when we stop, 2 times 3. Okay, once again, if I factor a 2 out, that's going to be 2 times 1 plus 2 plus 3. And of course, that's equal to this we just saw a minute ago. Of course, is 2 times 6, which of course is 12. But then this is equal to 2 times the sum of I equals 1 to 3 of I we did just a moment ago. Right here. As we saw, that one was equal to 6. Okay, so that's where that comes from. All right, let's take a look at the next one. We may not explain both of these. Let's explain this next one. Okay, so number 3, this property says we have, once again, the sum from I equals 1 to n. But this time we're doing AI plus BI. Okay, so if we put those terms, so when I is equal to 1, we have A1 plus B1 plus, when I is equal to 1, I is equal to 2, we have A2 plus B2, and then I'll do it here, plus dot, 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 plus up to the nth term, which is A to the n plus B to the n, when I is equal to n. Okay, now, so what we can do then, remember these are just little dots indicating we continue. So what we can do is we can rearrange this. Remember the addition, I can rearrange anything however I want to. And so if I do this, that's going to be A1 plus A2 plus, take all the A terms, plus all the B terms, arrange them, collect them together, B1 plus B2 plus dot, 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 plus B to the n. And of course, this is just going to be, the first part is just the sum of I equals 1 to n of AI. And then the second one is plus the sum of all the terms from I equals 1 to n to BI. Okay. And then finally, I'll just simply say that the fourth property here works the same way. Okay. So number 4, the sum from the series from I equals 1 to n of AI minus BI, okay, works the same way. Okay, since you collect all the AI terms, this case might be positive, collect all the BI terms, which are negative, and basically you can do it the same way. Okay. Now, let's take a look at a few more properties, a few more rules, and then we'll actually look at some examples. Okay. So here, someone has actually gone through and determined that if you add like the first n terms together from first few numbers, like I equals 1 to n, when just I, like we did just a minute ago, except go to as many as you want. Instead of 3, go to, it can be 10, 20, 100, 1,000. It actually turns out to be this formula is actually correct. N plus n times n plus 1 times 2. Okay. So, and that's actually quicker. That's, if you understand that, able to do that, that's actually much better than actually trying to do all that by hand. Because you want to add the first 100 numbers, that would be a pain. Okay. So let's do some more examples. I'll just say find the value of the series. Number 1, let's do this. If we wanted to do the sum of I equals 1 to 100 of I, okay, of course that's going to be 1 plus 2 plus 3 plus dot, 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 plus all the way up to 100. Okay. Now, obviously that would take a long time to actually have to add all that up, but according to this, from the rule we have, this is equal to n times n plus 1 over 2. So 100 times 101 over 2. Okay, and let's check that. So 100 times 101. So that's equal to 10,100 over 2. which is equal to 5,050. Okay, now if you want to check that on your own, you can, but basically that's the answer. And that's obviously a lot easier than having to add all those numbers up by hand. Okay, then we also have similar series for I squared and I cubed. Now, finally, let's put all this together in a couple examples, a few examples. Okay, number 2. Let's say I want to do the sum from I equals 1 to 3 of 2I minus 1. Okay, now this is one, and let's actually do this in both ways. Okay, so let's say one way is we actually do it directly. This is a shorter one. So when I equals 1, we have 2 times 1 minus 1 plus when I is 2. Here I is 1. When I is equal to 2, we have 2 times I is 2. So 2 times 2 minus 1. And plus when I is 3, and this is where we stop, we're going to have 2 times 3 minus 1. Okay, let's combine all those. So it's going to be 2 minus 1 plus 4 minus 1 plus 6 minus 1. And if you combine all that, and here's kind of in order you go in. So 2 minus 1 is 1, plus 4 is 5, minus 1 is 4, plus 6 is 10, minus 1 is 9. Okay, now, let me also say, or another way, now that's okay for when I is equal to 3. But once again, if I is equal to 50, that's a really hard way to do it. So let's actually use some of these properties and rules we have over here on the left and see if that can help us out. Okay, so once again, let's write this down again. So the sum of I equals 1 to 3 of 2I minus 1. Well, what that equals then, we use this rule right here. We can break this up into the sum of I equals 1 to 3 of 2I minus the sum of I equals 1 to 3 of 1. Okay, you can further break that down. Let's go back up here. So here we have a constant times I. And this is going to equal here to 2 times the sum of I equals 1 to 3 times I minus the sum of I equals 1 to 3 of 1. Okay, and we know these. All right, so we can calculate these. We have 2. Now this, we can use this formula here. This is I, n is 3, and so this is going to be 3 times 3 plus 1 over 2 minus the sum right here. This one is just a constant. There's no I here. That's basically this first example. And so that's going to be n, which is 3 times 1. Okay, let's put all that together. We'll see we get the same thing. Okay, 2, this is going to be 3 times 4. 3 times 4 over 2 minus 3. And so that's going to be 3 times 4. It's going to be 2 times 12 over 2 minus 3. And let's finish it off here. Or so you can actually cancel the 2's out. 12 minus 3, which is equal to 9. You check? That's exactly what we had up here. Yeah. So once again, this is a perfectly fine way to do it if you have small numbers. If you have a big number like this is to 50, it's much better to do it this way. We know how to do that. Okay. Now, let's do a couple more, maybe 1 or 2 more. What number am I on? This is number 2. Number 3. Let's say I want to do the sum from I equals 1 to 5 of I squared plus 5I. Okay, once again, you can do this each individual term. So plug in 2, plug in 1, plug in 2, plug in 3, and do it that way. Let's use these rules. Properties. Okay, So we can use this rule here. It's the sum that says by adding here, we can break this up into the sum of I equals 1 to 5 of I squared plus the sum of I equals 1 to 5 of 5I. Okay, now this first one, let's go down here. So this is equal to this. So this is equal to, according to this, where n is 5, this is going to be 5 times 5 plus 1 times 2 times 5 plus 1 over 6. Plus, now here we can also pull the 5 out. That's that rule right up here. So have a constant times the I. We can actually essentially factor the constant out, pull it out front. And that's going to be 5 times the sum of I equals 1 to 5 of I. And we also have a formula for that, this formula here. Let's just start to simplify everything. So we have 5 times 5 plus 1 is 6 times, that's going to be 2 times 5, which is 10, plus 1 is 11, divided by 6. Okay, make sure all that's right. Then plus 5, and then times, n once again is 5, so we use this formula for this one. So times 5 plus 1 over 2. And then let's just work on simplifying this. Okay, in this case, we actually cancel the 6's out. At 5 times 11, which is 55, plus, this is going to be 5 times 6 over 2. So we have 55 plus 5 times 30 over 2, getting closer. 55 plus, and 5 times is going to be 5 times 15, and 5 times 15 is 75. So 75, so 55 plus 75 is going to be 130. Okay, so 130 is that sum. And once again, if you want to check, you can always do it the longer way, which is actually to add all those terms up and do it that way. You'll see this is also correct. Okay, so let's kind of review what we've done. And actually then, however many terms you have like this, if you have more terms, if you have, this is I squared plus 5I plus 5, you just do the same thing. So break them up to 3 parts and then just do each part separately. Okay, so let's review what we've learned so far today. So we learned is kind of review what a sequence is. A sequence is some usually list of numbers, usually created by some kind of formula or some recipe. A series is basically where you take those numbers and add them together. We're learning about the notation of sequences to make sure you understand how that works. A sequence or series can be finite or infinite. If it's finite, it comes to an end. If it's infinite, it keeps on going forever, and that can actually settle down to a number, or it can actually get really, really big in either positive or negative direction. Then we learned about these rules of summation properties of series rules that actually help us to more easily evaluate series. And also, one reason why this is useful is that those of you who intend taking calculus in the future, you'll learn that pretty much any function can be written in terms of a infinite series using these same principles. So that's why it's important often in our math. Thank you. Have a good day.